Recording is on.
So we realize that most people don't really do all this. So we plan to, so the initiative here is to bring this thing to the students, show them what is going on in the hardware space, in the engineering space, show you how to design things. If you wanted to do something, we'll show you how to practicalize and how to develop product, how to be a designer, just how to really get your hands on things instead of just knowing the theoretical basis of things, which is not really ideal for someone that wants to practice these things now. So yeah, that's really like the why of why this hub started. So in summary, the hub started to develop people in the hardware space of things, to develop people that will be practitioners in their field and not just deviate to something different. If it's not that being a web developer, being a graphics designer, being like all those things are bad, but if the trend continues, it means that long term, in the long stretch, we won't really have. If I don't know whether currently we have a solid building, technological building foundations in Nigeria, for instance. But we can start from now to like develop ourselves so that because now we are the futures of this country. And mostly, there's one thing people don't really the white people don't really tell you about tech. Now we are most like I said, we most likely drift to the software part of things. But really, really, if a country wants to develop through technology, is most likely going to be in the hardware space of things, in a place where you can actually create physical things that can be seen. Because that's really what is going to change the society, not really just software and things evolving in that kind of place. So who is this hub for? So basically, this hub is for people that want to like test their hand on things. People that had a dream that I want to be a builder, I want to be a creator. I just don't want to be a product user. I want like you saw in your house, you saw fan, you were like, I wonder how this fan works. I wonder how this thing rolls. Or you saw smart systems, you saw smartwatch. You wondered, you just wear this watch, but have you wondered how this watch actually work? If they tell you that okay, this is a heart and beats checking machine, a heart rate checking machine, a blood BP checking machine. How do you like? Some people want to be entering that. Yeah, how does this actually work? How can this be built? This kind of thing. So this is who this hub is for people that want to build, people that want to do things in the technological space, people that want to be creators. You have this idea, you want to be an inventor, you want to create this next big project. This hub is for you. This initiative is for you. This space is for you. And like I said, seeing that the youth is the future of this nation as a whole, our main target audience are really the youth, young people to the youth. Those are our target audience. We are not really just targeting people randomly. We're targeting people in these spaces and most likely people that are involved in STEM, that is science, technology, engineering, and mathematics. People in those areas, those are the people that this hub is trying to target. People that want to be practitioners. Yeah. So who founded? So let's meet the founder of this hub, the person that actually had the vision and decided to just take the bold step and create it. So the founder of the hub is is actually me. That's yours truly. This is one for Nikachiko Marvelous. That is my name. Yeah, that's my name. And this, like I said, I saw this. Let me use it from the founder's point of view. He saw a problem and decided to like create this create this initiative. Now, personally, Onedika one for has done some things in his times. He has done some educational spaces for students in his faculty, in his university, on Python development, on embedded system development, on product development, a whole lot of things. He's a leader, he's an innovator. He has personal projects that he has embarked on. He's a team builder. He has worked around projects with people in the past and even currently. And he's a teacher and instructor. Like I said, he has embarked on teaching platforms in the university, teaching his classmates, teaching faculty members, teaching in societies and other things. He's also an enthusiast and practitioner within the specialization of robotics and automation. That is his core field is actually in the robotics and automation space. And he to getting to even become, like I said, he came to school to study how to be this thing, to learn how to do this thing, but unfortunately saw that it was not really practiced the way it should be practiced. And since that time, he's self learning and teaching himself and seeing that okay, there's the problem that people are not really that people don't really have that kind of mindset or courage to want to go and learn this thing or find this knowledge on their own. So he's trying to So the whole idea is trying to bring this thing to the table the best way he can with the team and people around him. So our vision, the vision of the hub is to be leading tech hub globally that will drive innovation for better, sustainable and reliable future. So like I've been explaining for you, the main vision of this hub is just is to develop innovators, to develop innovation, to develop products, to develop people that will drive those products, to lead in that space. And we can't really do all this without you, without your commitment and without your will to want this, to actually want this thing. Because if we all sit down and just look and nobody really does, like I mean, it's beautiful to join the community, or it's beautiful to want to join a program, but what is really going to make you part of the vision or really going to make you count? Because whether you decide to join or not, or whether you decide to take it serious, the vision is going to happen. The vision is going to happen. The question now is now: are you going to be part of the people that are going to join the vision? Are you going to be part of people that will drive in this vision? Are you going to come with the mindset to actually want to do something, to actually want to make a change, to actually want to make a difference for yourself and for your community and for the nation as a whole? Do you want to be part of it? And that is, so our vision is to bring those people in and to lead them, to direct them, to show them how to do this thing so that we can all together build a better future globally for ourselves and for our community. So in this hub, now like I said, this hub is not just random. Now it's not like we just do things randomly. Like today we can say let's go and do something in UI. Today we can say let's go and do something. No, we have like our core technological focus, which means that anything that does not revolve around these technologies, then we're not going to cover them. For instance, now our focus is on embedded things involving embedded systems, things involving Internet of Things, things involving automation, things involving robotics, things involving artificial intelligence and computer-aided design. So it means that if you are here and you don't see yourself in this field and you don't want to see yourself in all these field I just mentioned, this hub might most likely not favor you in the long term. I will just be sincere with you. You get, this is not the space for um let's say web, let's no web, let's say maybe you want to learn blockchain technology and things like that. This is not really the space for that kind of thing. If you want to be a pure software engineer, you want to know how pure software works, this might not really necessarily be the space for you. You get, so it means that if you are not in these areas, then this hub will not really favor you, or it will not work for you. You might not really find it interesting, you might not find the things we do or what we offer very interesting. But if these are your core, if these are the things that you want to develop yourself in, or you say that whatever you want to build in the future, one of these technologies is very important in what you are trying to do, then this hub and what you are trying to do is really what is for you. So yeah, our division now in this hub we have two major divisions. We have the educational aspects of the hub, and we have the product design and development aspect of the hub. So in the sense that like now, for instance, now this the community that we have currently on the WhatsApp group is majorly falls under the educational aspect. Now the educational aspect is the part where we try to develop people. Inside this aspect, we host workshops and tech programs. There's mentorship, there's project guidance. Let's say you have a project in mind that you want to do, but you don't really know how to go about it. You can reach out to us. We can assist you on it. We can mentor you on it. Then just like the training we're about to do today, we also it also falls under the educational aspect of the hub. Then for the product design and development part of the hub, this is where the hub creates in-house products. Let's say, for instance, now this project we're about to do, let's say it's something that's very interesting. We can actually now develop it as a real product that can be sold in the market and shared in the market. That so things evolve. So that's what really falls under the product development. And also the product development side, there's also the part of component sales, in the sense that now this most of the things you want to build now, you most likely want to need a real hardware or real components. So also the hub can also assist in fetching these things for you. So that's more of what happens in product design and development side of things than the educational side of things. So those are our main two core divisions for the hub. So yeah, so far social media wise, we are just on two spaces at the main time. So we are on the WhatsApp space, which I explained now that the WhatsApp space is mostly for the community. That's the people. That's what the WhatsApp space. Then for LinkedIn is just general for our professional postings. and other things. And if you want to follow us on LinkedIn, the name on LinkedIn is Incubator Hub. Probably after the meeting, in case you're not in any of our communities, I will probably share the links to both the WhatsApp and the LinkedIn aspects of the hub. So before we go into the next session, which is the building session, I just want to know if anybody has any question so far concerning the hub. If you want to ask anything, if you want to know what if you want, like if you need more explanation in what we are trying to do or what we are trying to do, you can just raise up your hands in the next 5 minutes so that we can answer questions. If you want anything to be clear, anything that you want to ask now, this is the best time to ask. So just raise up your hand if you have anything at this time that you want to ask so we can answer you. So we will take these questions in the next 5 minutes. Thank you. I'll be waiting for the responses. If there's no response, we carry on to the practical side of this meeting. Okay, Samuel, please can you ask your question? The floor is open to you, Samuel. You can ask your question.
Good evening, everyone. Hello, good evening, everyone.
Yeah, good evening, Samuel.
My name is Samuel. Mm, I'm from the Department of Mechanical Engineering. I have a question concerning you said about projects, helping out in project and all these things. So my question is, in terms of computer aided design, that's free card. Will there be any project that will be assisting of, like, let me say, if you know how to design as with free card, all this, is there any project given to someone that they will give to someone as a community member?
Mm,
Do you get my question?
okay, you're trying to ask that let's say somebody in the community needs a work to be done for them, or there's an opportunity for someone to do something and you have the skills to do it, whether we'll bring that offer to you. You're
Yes,
trying to ask.
yes, yes,
Yes,
yes.
yes, why not? If we see an opening for something that somebody in the community can do, we'll obviously do that. I don't know whether I don't know if you're currently in the community group, but I think as at last week, something I saw a completion for something called engineering engineers, and I asked for a request on the group if anybody was into welding and fabrication, and somebody actually answered that it was into welding and fabrication. I actually came to my DM and we talked on moving forward and developing that team to go for that competition. So that's just an example. So if we see something that people in the hub can be interested or people in the hub can be involved in, we will obviously bring it to the table. People in the hub, we bring opportunities to the hub. I
Okay, okay.
hope you are fine with that answer.
Yes, yeah, okay, okay, okay.
All right, thank you very much, Samuel. Any other person wants to ask a question or open for questions? Anything you need clarification on before we go to the practical session? Okay, so I think nobody is asking question again. So let's go into the practical session. Now, this practical session, I just want to say it on time. We're not due to current like where I am currently. I'm not currently in school. I'm currently at home, so my components and my kits is not with me presently. They are in school, so most of the things I'm going to do right now is going to be simulation based. Even though, although this is not a disadvantage because whatever we do here, whatever we do in this simulation is really what we're going to do in the practical. In fact, the software we're going to use is Pro Tools, and the reason why we're using Pro Tools is because it is more real to life compared to other ones, and I think it had the most components that were physically available that will really aid what we are trying to design. So yeah, so this is going to be a simulation based project, but it doesn't mean that whatever we do here can't be done in real life or can't be done with real hardware. It can be done exactly with real hardware as long as you follow the steps. And like I said, this meeting is being recorded. So if in the future you want to practice this thing or you want to like on your own build it, you can reach out to us. We'll tell you the components that you can specifically buy for it. Then you can go ahead and watch the video and just follow steps, or you can get Pro Tools and any necessary thing to like run simulation and just learn simulation based. And that reason why we are trying to do most of our practical sessions in simulation based things, because we notice that people tend to get find it hard to enter into the hardware space because of the money to buy physical components. So we're also trying to also use this medium to introduce you to simulations, so that in case you have a project idea but you don't have the money to afford what you need to buy, what is needed, this simulation software can actually be a kickstart for you to actually start learning all these things before you can now make some money and or gather up some money and start practicing with the real stuff. So yes, let's so back to the PowerPoint slide. So what we are going to be creating basically is is so yeah, we on the community group chats we did a vote for we gave three project ideas of what we can build, and you guys you guys chose a design of a smart fan regulator using real-time temperature. Me, I was actually surprised on what you guys chose. I was mostly thinking you guys were going to choose the walking stick for the blind, because I don't know, I feel like it solved a problem that was more realistic. Not like this one doesn't solve a problem, but like it felt like it would have been more interesting to embark on. And and actually based on what I know I would have done for that thing is way more compared to what I'll be able to what I'll cover for this year, because that project would have had a lot of components and a lot of things to go over. But since people chose fan regulator, who am I to who am I to say to not give you what people want? So basically, this sketch now is a sketch that I drew. Sorry about my bad handwriting and my bad my bad sketch and my bad handwriting. And they've been telling my handwriting is very bad, but what can I do? Engineers usually have bad handwriting because we're mostly thinking, we're not really thinking of how fine our writing is. We're just thinking of drawing rough things on the paper. So now before we even go to the practical session, I'm going to teach you people some key things to like some key things to really understand before you go on the project, what you should really do. So yeah, if you noticed, I did not just start this project up by building something off of imagination. I actually drew a sketch of a physical product of how I wanted it to look like. So it means that when you're trying to design something in the engineering space, you should first go to concepts, conceptualize your idea. How do you want this thing to be? What do you want the use case to be? So for instance, now this fan, I thought of there are different types of fan in this world. There's fan in your house, in your parlor, all those ceiling fan. There's standing fan. There's handheld fan, those small fan that you said these days. There's even table fan you can put on the table. Maybe you have a reading table and things, whatnot. So there are different types of fan and different kind of use case for what you can use this fan for. So I felt like being that we are students, a fan that can be useful for us or generally that can, and also since you guys are mostly beginners in this kind of things, to not really kind of blow your head off with a lot of technology, I decided, okay, let us make a table fan. That is the fan that like the project idea is to make a table fan that you can put on the table. Maybe a student you're reading, you fan that will be on your table. And instead of it just being a random selection of this thing using buttons to change the speed, it's going to be automatic based on temperature. It's going to change the speed on its own based on what the temperature of your room or your environment is going to be. And the reason why we're also even making it smart with temperature based changing is because of and now you know when you are working with a fan, the more you increase your speed, the more energy you are wasting. That is maybe your battery energy, or if you're using your NEPA light, whatever energy you are using. If you just power, let's say your room is already cool enough for it to be conducive for you, but you're not instead you're wasting a lot of power on this fan at its topmost speed. It's not really ideal. In fact, a good example of this is your ceiling fan. Imagine your ceiling fan in your house was automatic. It ran based on what was needed instead of just putting the highest number three or number five, which is wasting a lot of power in the house. So this kind of innovation, this kind of idea can solve the problem of power wastage basically. And also it saves you the hurdle of changing your fan speed. Your one is just to on fan and focus on whatever you came to that your reading table to come and be doing. Whatever your fan wants to do, to do it automatically based on this thing. Then also, so yeah, so this was the sketch design I came up with, and the things I labeled are the major things the fan should have. And if you notice, if you look here, I added a touch. which was I just make the fan more fancy and more like I said. You know, I told you that the use case now for this fan that we're trying to develop now is a reading table kind of fan. So I said, why not kill two birds with one stone? On a reading table, most people, as a student, you most likely read in the night. That's me personally. I most likely read in the night because it's very quiet at that time. And sometimes there's either no light in school or light in the hostel, wherever you might be staying at that time. And everywhere might even be hot and everything. So this project kind of kills two birds with one stone. So it means it's giving you light at the same time also giving you like fresh air so that as you're reading that calculus or that ODE or that first order differential you're doing, your head will not boil off. So yeah, so it's killing two birds with one stone. So also since I just said that we don't want this fan to run based on NEPA light, so that in case you don't have light, you can always switch your touch on. So it means that it's going to be battery powered. It's not going to be socket powered. This is going to be a battery powered project. So yeah. So you see that before designing the thing, you see that I'm coming up with design concepts and design and ideas on what it should be for and why it should be. So if you see that the main thing that there's a fan, there's a touch. For the touch, we have a touch switch. Then if you look at the bottom, this is the on and off switch generally for the fan to turn on and off the fan. Then there's a light that will be here for power indication so that you know that your fan is actually on. Then the temperature sensor is going to be around here. We don't want the temperature sensor to be close to the fan so that the fan's temperature will not directly affect the temperature of the so we kind of put it far off. See, that's another design choice again, like I said. So we know that if the fan is blowing, it means that if the sensor is too very close, or maybe in this area of the fan, it might influence the temperature to be colder than it actually is. So that's why we kind of put the sensor in this bottom parts of the design so that it doesn't directly influence, so that the wind from the fan doesn't directly influence the temperature reading. So you see that's another design concept that we just came up with, and that like idea on designing. Then if you look at these three lights is our speed indication. Now I was thinking of using an LCD, that's a display to be showing it. You know, most modern fans now have displays instead of just showing lights. But we just want to, like I say, we want to keep this project simple and easy for people to understand so that you don't get all like boiled up in your head trying to understand what is going on. Because you're going to see a lot of things you have never seen before in this project. You're going to hear a lot of things that never even make sense currently for now. But as you keep on practicing, it will make sense more small. So we try to make this product very, very simple. So instead of using a display, we used light to be showing. So there's light to show speed level one, light to show speed level two, and light to show speed level three. So that's basically so you can see that we have our concept of our design. We know what we're trying to do. We know that this is a table reading fan with a touch and it's temperature controlled. We know that this is going to be direct current powered, that is battery powered. And also, when we're designing, we're going to like put all this into consideration. And we know that we're trying to control the speed of the fan. So these are the major aspects of the things we need to know before we can actually start building something. So now that we're done explaining the concept of the design, now let's go into the. Now there's something I didn't write here. After you design your concept, the next thing to now go through is your on a good day, this was a full engineering design. After this concept, you now actually probably go and do the CAD design, the computer design of how the structure should look like, the chassis and every other thing. You do your electronic design, that's your hardware design, then for your firmware design, that is the programming of the code. There's going to be logic, because this is a smart system, so you need programming to deal with it. This is not just pure electronics, so you need to program. That's why it's called embedded systems. So let me just explain what is even embedded system. So basically, an embedded system is a computer built for a specific task. Unlike your laptop or your phone that can do a lot of things at the same, or is not really tailored to just one common task. Embedded systems is a computer that is built for just one common task, and they work with real-time data. For instance, now maybe a good example is, I don't know if you have seen most of these smart lights that when you are going under in the midnights, by the time you reach close to them, they shine brighter. Then when you come out of them, they kind of go. Most of the time, some of them are either pure electronic, or some of them, if they're smart enough, they are embedded systems, and their whole task is just be offing and on that light based on presence of somebody. There's a sensor there that senses a person, then knows what it's going to do. In fact, the whole heart of embedded systems are the computer, the chip itself, the microprocessor you're going to be used programming, the sensors and the actuators you're going to be working with, and your firmware. By firmware, when we say firmware in the hardware space, we just technically mean code or your programming that's going to actually be the logic or the control behind, like the instructions behind the smart system. So yeah, so let's head over to the simulation software so that we can start this project. Good day. So now we are going to continue on our project on creating our smart fan that is going to be regulated based on temperature. So the former video we did before was unfortunately wasn't clear, so we had to re-record. That's why we took time to release the video out. So now let's go straight to the project. So this is the circuit diagram that we are going to be using. Like this is the circuit diagram of what we are trying to create. So this is the fan that we are trying to control. It's being connected to a motor driver, which can help us in regulating the speed, and it's also connected to a nerve controller, which is the brain that receives signal from that receive the temperature reading from the temperature sensor. It gets processes this reading, then controls the motor driver, which then controls the fan. Other circuit elements are the battery, the switch to turn on the whole system. This is the speed indicator light to show whether it's in speed level 1, speed level 2, or speed level 3. There are three major speeds we're trying to use here. This is the power indicator light that shows that power that when you on your switch to turn on, so you know that your fan is actually on. Then there's, as an addition to the project, we also added a torch so that the fan adds no initially we said that what we're trying to build is a reading fan. Imagine this is a reading fan for a student, as most of us here are students. So this project is, imagine it as being a reading fan that you can be using for yourself. You can create it yourself, because now if you notice how this the way I created the circuit diagram, I created the circuit diagram in such a way that the components, that if you want to buy these components, actually create it yourself. These are how the components actually look like in real life. So you see, these are the fan is going to most likely look like. It's a 12-volt fan. These are the temperature sensor DHT11 is going to look like. These are the microcontroller, which is Arduino Nano, is going to look like. The motor driver, which is L293D, is an IC, is an integrated circuit. This is very smooth. This is looks like. The switch is looks like. The battery is a lithium ion battery. That's 18650 lithium ion battery. You put three of them to give you that 12 volt that we need to power this motor. These are the LEDs. These are, so if you want to build this project, like like to as a instead of just because we're going to focus on simulation here, so that everybody can easily follow if you want to just quickly build without being constrained of having to go and buy these things. So if you don't want to see how these things work without actually start without spending money yet on embedded system, that's why we are trying to work with simulations for now. So but in the circuit diagram, the way the way we built the circuit diagram was built in such a way that if you want to actually make this thing, you can actually visually see how they actually look like, so you don't like get the wrong components or the wrong things. So yeah, as I said before, this is an additional component, which is a torchlight, so that your fan is not just a fan; it's also a torchlight in case there's no light in your environment when you're trying to read the night or something. You can always on the torchlight that is attached to the fan. So this is an additional circuit to just make our fan more unique and more interesting than it already is. So without wasting time, let's head over to the software where we actually run we'll do these connections and send the code to it and run the simulations to see how everything works out. So let's go. So we're going to be using Pro Tools for this, and yeah, the elements, that's based on what we based on the circuit diagram. Based on the circuit diagram, let's get our components that are needed for this project. So we firstly need an Arduino Nano microcontroller, which is this guy here. Mhm. So this is the Arduino. Then we need a temperature sensor, which is, as I said before, DHT11. This is our guy. Get the DHT11. We also need the fan itself. We need a fan. I see I have different models for fan. Okay, this looks mostly like what we are trying to do here. Let's get the fan. We need the motor driver, the circuit L293D IC circuit. So this is the circuit. So I'm just going to speed up the video now so that I can get the many components, and we'll come back to wind them up. Okay, so we we are done with placing the circuit components on the circuit so that now we can start with the connections. Now, now to start with the connections, we will okay, well, okay. I think let's first connect the sensor. Let's first wire the sensor to the the microcontroller. I won't really go into too more details on how the wiring works, but basically in electrical connections, how wiring works is that they usually they are majorly there are two terminals. The side where you send your power to, basically we call it positive, and the side you send your the the negative side of your power to, which is negative. But now now if you notice most of the time I have that two parts, either the positive or negative. But since like our sensor and our motor driver, they have more pins that are more than that positive and negative. So in this sensor, for instance, it has a data pin which goes to one of these data pins that we can use for processing. When you are programming it in the microprocessor, same thing goes for the motor driver. He has extra pins that are not excluding from the power pins that can process your signal and other things you are trying to do. So let us start the connection. So this is the voltage side. This side is meant to go to 5 volt. This side is meant to go to ground. This is the side that goes to the microcontroller's data pin. So let's take it to pin 12. Let's take this guy to pin 12. Okay. Then let's go to the power raise and get a ground power connection. So we can put a ground here. Then let's also get a power. This power just signifies that 5 volts is going to it. From our circuit diagram, you know that the 5 volt actually comes out from this place of the motor. This motor driver has a place where you take something not higher than 12 volts and put into it. Then the voltage regulator within it reduces it to 5 volt that you can send to your motor controller and other things that are controlled by 5 volts. The 12 volts is necessarily for the fan itself. So yeah, that's but this connection I'm just trying to do is just to show you that this is 5 volts. I don't want wires to be moving to be everywhere. That's why we first did the circuit diagram so that you see how the circuit actually looks like before we now actually do the main thing. So sorry about the rain that is disturbing the rain. I think the rain might be disturbing the audio. Unfortunately, rain is falling where I am currently. So yeah, so this is the ground connection. We have successfully connected the sensor to the microcontroller. Next up, let's connect the motor driver. So firstly, I would like to connect 12 volts to this guy. There the switch. So that's our power source. That's this is what acts as our voltage source, which we're going to modify. By default, it comes as 1 volt, but we're going to change it to 12 volts. So yeah, so it passes through the switch. Then let's ground this guy. Let's put the ground. That is the negative side, like I explained for you us before. So yes, okay. Then we can put this power in the 5 volt to indicate that power. You just know that anywhere you see this sign I'm using here, just know that they are all connected to themselves. Anywhere you see them, and anywhere you see the ground terminal, just know all those grounds too, they are all connected to themselves in the whole connection. This is what we do usually in schematic or simulation software so that, like I say, wires will not be everywhere. We use their symbols to indicate that okay, if you see anything like this, it means that they are all connected to themselves. And this is a symbol for power. This one too is symbol for ground, which means they are all anywhere you see they are all connected to themselves in the ground terminal. So so let's take so basically how this motor driver works is that it's a two channel motor driver, which means that it can actually drive two motors independently. So assuming we're using but since we're using just one, we're trying to control just one motor, it's just this top side will be associated. We won't associate with this bottom part. So yeah, like I said, I won't really go off time and I won't really go into details on the circuitry and the electrical connection of how some things do. I will just maybe briefly explain them the best I can to save time and everything. So this enable so there are three signal pins, then there are two output pins. Now the output pin now these are the ones that these are the way you connect to your motor. Now usually there's nothing like positive and negative when it comes to motor. How you connect your motor is going to determine how current is going to flow through it and how um, it's going to rotate. For instance, the way we're trying to connect it, if we're connecting output one to this side and output two to this side, which means the motor is going to flow in a clockwise direction. As we put the wire the other way, the motor was going to flow in the anti-clockwise direction. So okay. Then let's connect the signals to the microcontroller. Enable. Now for you to be able to control the speed of the motor, you need to connect it for the first channel to enable one. So let's and there's some and what about motor? How motor work in its microcontrollers is because motors are usually digital based, they're either off or they're on most of the time, right? And if you want to be able to control that speed, there's something we call pulse width modulation, which is trying to fake an analog signal because for us to get leveling in control, we need analog signals, not really digital signals are either one or zero, that's off and on. But when you see this fan, we're trying to control it in different levels. So we need to simulate or fake this analog signal with digital signal, and that's what we call pulse width modulation. You can do your research and check more on what's pulse width modulation. So basically, it's just us trying to off and on the device so fast that it now averages out to a voltage. For instance, now the highest voltage for a digital signal is 5 volts, while the lowest is 0 volt. So if you are running a pulse modulation, depending on how fast and the duty cycle, how you're often and on it, not also of like literal hard computer often and on based on the program and everything. It determines the voltage that it's average at, whether it's average as 2 volts, average at as 3 volts, average at 4 volts, and as averaging out as those different voltage levels is going to be increasing or reducing the fan speed. So yeah, so to really get control of that speed control, we need the enable pin. And one thing about all these things is that you need to make sure that they're actually connected to pulse width modulation supported pins on the microcontroller. If you check for Arduino Nano, there are many pulse width modulation supported pins, but the one we're going to use for this project are pin 3, pin 6, and pin 5. Those I've checked before I did this and noticed that okay, those pins are actually supported. Mm, so yeah. So let's connect enable one. I'm coming. I've forgotten what I put enable. Okay. So let's connect enable one to the digital pin 6 and enable two to digital pin. Sorry. Enable two to digital pin 5. So yes, so this is basically all for the motor control side. So the main circuit that should concern us is the indication lights and the touch. Let's quickly do the touch because the circuit for a touch is not too complicated. I'm trying to move this switch a bit down so that there's space for other things. So yeah, I think it's okay where it is. So for this touch, we need three of this guy actually. We need three. So let's copy them 3 times. Okay. I'll see maybe shoot this guy down a bit. So let's connect this. This resistor is going to go to the switch so that it's now the light is going to be on. Based on when it's switched on. Connect this. So this is actually a parallel connection. The reason why I'm doing a parallel connection is so that regardless of if any of the voltage flows through three of them differently and not in series, because something like this now you do not want to program you do not want to connect them in series because of a lot of reasons. For instance, one, if one of the lights is not good, you still want the remaining two lights to on. That is one of the reasons why you want them. And also, it's just for this situation base is the best way and the most efficient way to connect them is actually in series and not in parallel. So that's why Sorry, we're connecting it in parallel and not in series. So the best way to connect it is in parallel. Parallel just means that when I connect them back to back to themselves, we're connecting them in a way that voltage can flow through them in different ways. Now, voltage comes from here, it flows to this guy in his own part, it flows to this guy in his own part, and it flows to this guy in his own part. So if, for instance, this circuit, something happens to this light, it will not stop these two lights from on. And if this one, something happens to this one, it doesn't also stop the other one from on and vice versa. And it's just and it's good practice in this kind of connection to connect them in parallel. Then the last thing to connect here should be there are two things, the power indication lights. Now this power indication lights, normally I'm meant to connect it to this place for the 5 volt, but I want to just I want to describe something later. That's why I'm putting it in this bottom side. When the time come, I'll explain what I was trying to describe as it will make sense. I think I will just speed up the remaining connections so that we don't just don't let me just speed up the remaining connections in this point. Okay, so basically we're done with all the connections that we need, and what we just connected was we connected this the power indicator, that's the green LED, to a resistor and to power, so that when this is activated, the LED comes on, so you know that the circuit powered on. Then for the indicator lights, we didn't power them to the power source straight. We took them to digital pins 8, 9, and 10, so that we're going to be able to program for the system to know when is to on this LED, to on this one, not on this one, to indicate that it's in level 1, level 2, or level 3. So now one more thing we're going to do is that all these resistor values now, these are the default value they came with 10k, 10k, 10k. But realistically, this in a realistic manner, this doesn't make sense to just use resistors just like that. You actually need to calculate the resistance value. And a good formula for calculating that resistance value is something that we all might know, which is your voltage formula, and the electricity, that V equals to IR. In that case, we make since we're trying to find resistance, we just make out the formula and to be V over I. And usually this LED, let me open this. Usually they usually have a voltage input of 2.2 volts and a current of 10 milliamps. So so if you do the calculation, that's 2.2 over that 10 milliamps, that's 0.01. It gives around 220 ohms. So to just create this as a whole number, instead of using 220, we'll just use, for instance, 300 as the resistance. So we'll just change all these ones to 300. Okay, so yeah, we're done with changing all them 300. Now, as for this one, we are not going to change this to 300, because now the reason why I put all this at 10, because they are just connected to one LED, so the calculation was the same for the. But in this case now, is connected to three LEDs that are in parallel. Now, usually in parallel connections, the voltage is the same, but the current adds up. In the sense that, okay, everything that's coming, the voltage is always going to be 2 point. If voltage transfer to be 2.2, if voltage transfer to be 2.2, 2.2. But the current, instead of being 10 milliamps, is going to be 30 milliamps, because there are now three of them. So it's 10 plus 10 plus 10, that is 30 milliamps. So if you recalculate everything, you get around 73.33. But to make the whole number, we'll just use 80 ohms as the resistance value for this guy. So you see that when you're designing all these things, there are some basic electrical knowledge you should actually understand to do some things, so that you don't blow up your circuit, or waste power and things like that. So basically, I think we are done with everything that concerns the hardware. Yeah, so let's move over to the software side and see how things work over there. So for the software, I've already written the code before now so that we can save time and not waste time, because if you write all this code and after doing the hardware explanation, it's going to take a lot of time. So I'll just quickly explain what each line of code is doing and how it affects our system. Now, generally embedded system is two parts: the hardware part of things and the software part of things. So basically, if you're going to be an embedded system engineer, you need to understand how electrical systems work in some kind of way. And also you also need to understand how software engineering works. And the programming language that is the most key in embedded system is actually C plus plus. So if you're going to like want to learn a programming language with respect to embedded system, I would advise you to learn things that concern C plus plus, and things that, and so also Python is also something we use very well in this field amongst other programming languages. But these are the most common language. So this is called an Arduino IDE actually, and it's actually an IDE that is used to program the Arduino's microcontroller that we're using here. Although the IDE can be used for other microcontrollers like ESP, STM. No, okay, actually STM. And I'm not sure it can work with Arduino IDE. I think it has its own dedicated STM cube. But my point is that, yeah, if you want to program this, you cannot, and you can also do this programming in VS Code, but you need a library called Platform IO. But the dedicated like IDE, that is integrated development environment for programming something like an Arduino, is actually the Arduino IDE that was made by the Arduino Foundation. So yeah, let's go move over to the code. So the first thing we're going to notice that, okay, now we're going to call out. Now we're trying to use a sensor. We're trying to use a sensor in this project, and is a sensor that reads value. So to make this easy, there's actually a library that the sensor has to be able to easily program the sensor, and that is called the DHT library. So we need to include this DHT library into our package. So that's what we are doing with this line of code. We're including the DHT library. Now, the next line of code is us creating the variables. Now, anytime you see hash define in an Arduino code, we are trying to define the pin numbers that we're using, or define the parameters we are trying to use in the hardware space of things. So we are defining the pin. No, remember that we connected the digital pin of the sensor to the Arduino pin 12. So that's why we defined it as the DAC pin as pin 12 here. Then you have to give it the type. Usually there are two types of DHT. There's DHT11 and DHT22. For this project we use DHT11. That's why we use the DHT11 type. So now you are going to create an object, just like in regular programming in Python. And then you create an object so that your system knows what this object is. Now, to create the object, we first call the library name, which is DHT. Then we name the object something. This temperature sensor, it can be anything. You can name it whatever you want to name it. This is the name of the object that you want to give. Temperature sensor just looks like the best name in the kind of project we're trying to create. You can even name it back as DHT, or name it back as whatever you want to name, but it's just wise to name it what should make sense. So temperature sensor is what I named it in this case. Then there are two parameters that this object expects from you: the pin that the object is connected to, and the type of object it is. So we connected, so instead of we can actually remove this whole thing and just straight up put 12 here and put DHT11 here, but it's good practice to actually use variables to do your things in case you want to change some things. You just change it from the variable straight instead of looking for everywhere you defined that thing and changing it through there. So us writing DHT pins is the same as us writing 12 here, pin 12, and us writing DHT type is the same as us putting DHT11 as the type here. So then also we're going to create a variable which is an integer. And usually in C, if you're creating variables, all this one from doing define, we're not actually creating variables with them, we're just defining their locations, that kind of thing. So this int now is a number based variable. If you want to, in the major variable types you will use here are either your int for whole numbers, your float for decimal numbers, your string for string, and char for character, then your boolean for true or false, which mostly is going to be used in your logical statements and things like that. So we're going to create a temperature reading variable. Now we won't store anything in the variable yet. We just close this for now because we're going to read it while in another part of the code, not here directly, because we can't read it directly in this kind of place. So other variables include the variable for the motor. We connected three sides of the motors to things: the enable one, input one, and input two. I know we connected in the hardware side of things, we connected it to enable one to digital pin 3, input one to digital pin 6, and input two to digital pin 5. So we're trying to match up what we did there because everything has to be consistent. Your hardware and your software needs to be consistent, or things should not really work well. So then this last part of variables is for the indication pins. We connected them to pin 10. So that's level 1 light is connected to pin 10, level 2 light is connected to pin 9, and level 3 light is connected to pin 8. So now in Arduino IDE, there are two major functions that always, like, if I try to create a new sketch now, they will even by default give me these two functions. There are two major functions that come with it, and that is your void setup and your void loop. So basically, your void setup is where I've created the variables for where these pins should be and location and parameters should be, but the system has not really been set up yet to the microcontroller, so the microcontroller will really understand what it's working with. So void setup is where we now set things up. Literally, we set things up. We call it. We take whether this pin now is it an input pin, is it an output pin, is it a signal pin, is it, like, are we using the serial monitor, which is the debugging interface when we are trying to use into of your console that you know in JavaScript or your terminal you know in Python. Here we call that one serial monitor. And then the void loop is now where you now put what you want to happen continuously. Now, usually embedded system is actually a computer built for a specific task that happens in real time. So it's consistently checking system variables consistently, like it's like a loop. It keeps on happening forever and ever, and doing what it's doing. So the void loop is now where we actually determine what we want the system. So for instance, now we want our system to be controlling the speed of the fan with temperature. So that code is going to be written mostly in the void loop, while setting up the temperature sensor and other parameters are going to be done in the void setup. So going back to the code, so we used so the major things we used there are three things. That's the temperature sensor, the motor, and the indication light. So these are the setup. So it's setting up the motor. Now we are trying to control something. Like, we are trying to control a motor, which means we're sending out an output and we're not trying to receive something. So that's why it's going out as an output in one, in two. The P mode is you connected that pin you connected. For instance, we connected in one to pin 3. So we're trying to tell the microcontroller what pin 3 is. We want pin 3 to act as an output pin and not as an your other parameters can be an input pin, it can be an input pull up pin. So we're creating it as an output pin. For majority of things in this project are actually output, except from the temperature sensor, which you don't even need to specify because it already came with a library, which you will now have its own predefined function. So in one, in two, the same thing, they're all outputs. The LED indicators, we also want to on them. We're not receiving signal from them, we're sending signal to them. So they're also output pins. That's what we did here for the LED 1, 2, and 3. That's the level 1, level 2, level 3 for the speed indicators. Then for the sensor, like I said, this is a library. So to initiate the library to be set up and to be activated while your code is going, what you need to do is just to call the name with a begin method. In programming, when anytime you see full stop, then a word with in brackets, then know that that is actually we're trying to call a method a function per se. You get, so this function is to begin, or this method is to begin or to initialize the temperature sensor. The temperature sensor, then we just put a little bit of delay of 500 milliseconds, because the time that the microcontroller is, it also measure time in seconds, it measure time in milliseconds. So 500 milliseconds is the same thing as saying half a second. So it's going to on for half a second and wait, then continue the rest. The reason why we're having that small wait is so that we're sure that, because computers are extremely fast. If you just without this delay, the thing might even it might not even turn on, and it just go to the next line of code and start working, and your code not really work well. So we just add this delay to as a safeguard, so that we'll make sure that the temperature sensor is actually activated before it moves to the loop side of the code. So before we go to the loop side of the code, since we are working with a lot of things here, it's just good practice to actually create your major things in their own dedicated functions, instead of, we could have all these lines of code now, we could have put them inside the main void loop. But to be more smarter and make our code more efficient looking, it's better to create them as their own variables. So we created I think four major variables. That's variable for speed control 1, speed control 2, speed control 3, and variable to and say functions. Function 1, the speed 1 function, speed 2 function, speed 3 function, and a function to turn off the fan totally, sometimes as a safety measure in case the environment is just too cold and it's not just recommended to even be turning on a fan at that point. So this is the function. To create a function here, instead of your JavaScript, you write, if you don't want this function to return back something to you, you use void, which means, if you notice, very setup and void loop are actually functions, and it begins with the word void to tell the to tell the program that we're not returning any value back for. Assuming we're returning the value back for, we will add the data type of the value. For instance, now if we're okay using a distance sensor, for instance, to calculate distance of somewhere to somewhere, instead of and we want to do a function to calculate that distance, instead of putting void there, we'll actually put an integer or float, but most likely an integer. Whatever data type your function is meant to return, you put it here. But our function is not returning it, so void, we put void, which literally means nothing, empty, like a void space is an empty space, like a space filled of nothing. So that's what void is just trying to do here. So in the speed one, remember I told you that in one is what majorly calculates the speed or gives the speed function when you're dealing with that motor driver, that L293D that we connected our hardware to. And you send an analog signals to it. And in Arduino, the analog signal has a range of 0 to 255. I think it's 16-bit or there, but if you calculate, I think it's 16-bit or there, but I'm not sure. You can maybe research on that later. But it's from 0 to 250, which means 0 is the most lowest analog value you can send, and 255 is the highest analog value you can send. So for the first speed, we send an analog value. This analog write, we're writing an analog signal to that in one, and it's at a level of 100. So out of that 0 to 255, we're sending 100 at first to the enable. Then we're turning on the indicator lights one to show that this is speed level one and offing the remaining two indicator lights. Then in speed level two, we're increasing that speed from 100 to 200 over that 255 to 200. Then we're on the level two lights and offing level one and level three lights. Then for the speed three, we're now increasing it to the highest. We're increasing in one to the highest, which is 255. Then from that, then after that, we're now on the indicator light three and offing indicator lights one and two. So you see that. So this is the function. Then to off the fan, we're offing everything. Digital writing in one, in two, digital write in one. The indicator light, all of them are offing everything because we don't want anything to be on again in the system at that point when the fan is off. You get. Now, if you notice that I off the in one and in two here, but I never actually on them in this function. The reason why is because I knew that I was always going to. Okay, I'll show you this now in the void loop. Now in the void loop, before I explain this side of code, this is where I actually on and off the in one and in two. Now, basically, let me explain for people that in this side of things, how we connect. There's nothing like positive and negative in connecting to a motor, right? What what does happen is that how you connect it and how you program is just going to form the direction of flow. So in the sense that we wrote in one as high and in two as low, it means that if it comes when the code is running, it's going to in if output in one is controlling output one, so output one the voltage is going to flow because it's high, voltage is going to flow through it. But now since this guy is low, no voltage is going to flow through, so it means that the source is going to go like this, enter it and go in that clockwise direction that you wanted. As we wanted an anti-clockwise direction, we would have put the in two as high and in one as low. But since we want our fan to operate like normal fan, clockwise direction, we put the in one as high and in two as low. So that is why this place is high and this place is low, to give that direction that we want the fan to flow in. And I knew that at all time I want that thing to always flow in that direction. So instead of always repeating or instead of repeating the code, this particular code in all the different functions, I just initialize it in the void loop itself. Then it means that by default, when it's running speed one, whether it's running speed one, speed two, or speed three, this code is going to always be activated. It's just the speed you want to be changing. That's why it's always like changing there. But in the part where we're offing the fan, I actually off everything so that no power is flowing to anywhere. So now this is now we created a temperature reading. In the beginning of the code, we created a temperature reading variable. Now this is now where we actually read that temperature. So to read that temperature, you call this sensor, and the method to use is read temperature. Now, now if you this method will read the temperature in degrees Celsius. If I wanted to read this temperature in Fahrenheit, for instance, all I just need to put is true inside here. If I should put true inside here, if I should put true inside here, it means that when the code is instead of bringing out the temperature in degree Celsius to bring out in degree Fahrenheit, but we want to work with Celsius because that's what we are used to. So we are using Celsius. Or let's say if you have in case you have a project that deals with Fahrenheit, you can just put true inside the bracket and to actually output your temperature in Fahrenheit. If you want to do other things like Kelvin or that temperature, you can just do the mathematics for it, get the reading in Celsius and
and write an equation in your code to convert it to a different thing like Kelvin or whatever other temperature conversion you want to do. Now, this sensor I use is actually a sensor for checking humidity and temperature. As we wanted to check humidity, the function would have used was read humidity. But this query does not concern humidity. That's why we're not using that part of the sensor. We're just focusing on the temperature side of the sensor. So it is read temperature. So now, this is now where the control logic now actually happens. So we're now saying that if any temperature that is above 30 degrees centigrade, we want it to, that is at that point we know that the environment is going to be very hot. So we put the fan at its highest speed. That is, put the fan in, we call the speed 3 function. That's this function that rotates. So it means that once this condition is true, this block of code in speed 3, all this block of code in speed 3 that they actually run. But if the temperature is less than that and in the range of 26 to 30, for this one now means that a range of 31 and above, that's what greater than 30 means, 31 and above. Now this temperature reading, else if it's in a temperature reading of greater than 25, that is in the range of 26 to this 30, it should read speed 2. But if is greater than or equal to 16, that is in the range of 16 to 25, that is at that point we know everywhere is cold. But so it means you don't really need the fan to be wasting power and be at the highest speed. So you put that speed one, which is its lowest speed. But now else, if anything is less than 16, it means at that point it has even turned to ice already. Like the environment should be like as if AC is even blowing you already. So we just want to even turn off the fan to save the battery, save power, and save usage of electricity and everything. Because at the end of the day, when you're creating devices, it's good to actually put saving of power and other things into consideration. So at that point, we just off that is else. If nothing, if none of this condition is met, that is, and for none of this condition is met, it means it's below that 16 degrees centigrade. So you want to turn off the fan. So that is actually basically everything in the code side of things. So you see that the code is actually very easy to understand and it's kind of straightforward. It's just like you trying to talk to the hardware. You have connected hardware wire. The code is not like you trying to speak to it on what to do and how to actually act and how to behave. So yeah, so usually if you're connected to a real hardware, if you're connected to a real hardware, so far we're doing simulation. That's why if I the one of the reason why I use Pro Tools because the way we upload the code in Pro Tools allow you to use the real IDE to actually write your code. Now the other just describe that if you're connected to a real hardware, after I've written your code, if the next thing to do is to actually go and select the type of microcontroller you're using. There are different microcontrollers. These are Arduino types of microcontroller. There are different Arduinos. The most common ones you will see around here is Arduino Uno or Arduino Nano. In our case, we're using Arduino Nano. Another popular microcontroller is ESP32, and these are different types of ESP32 you can connect. So whatever board you're using, you choose the board. So in our case, we're using Arduino Nano. Then you come and select your port. That's where because it's connected, the code goes through USB connection. So you connect your USB wire to the microcontroller and connect it to your laptop. Now, no port. This COM3 is not a real COM. It's just my general laptop COM3, like a general laptop peripheral. So since I'm not connected, there's no ports actually showing there. As soon as you connect a real hardware, you will see the ports. So connect to that port, then you will hit upload to send your code. But since we are not connected to a real hardware, what we just do is to verify the code so that the hex file will get the link to the hex file that will now connect to the Bluetooth to now work the code on. Let me increase this output so that I will see the hex file link in my directory. So you compile. So if as soon as your code is good and everything, so you see it's done compiling. So it has compiled. No, this is C++. It's a language that is based on compilation and not like Python that is not based on compilation. So yeah, so this is the hex file we need to run the simulation. So we'll copy this directory that has given us from. Now usually if you get Arduino IDE for the first time, your code will not actually come out like you won't really see all these extra things you are seeing. But in case you want all those extra lines to come out, you just come to your preference and your compile. Click this show verbose output during compile and upload. Tick them so that all these extra things that are coming. If I didn't tick them, all these extra things that come out will not come out. What will just come out is after I finish compiling, this place that says sketch uses 13% of the program, that's 13% of the memory. This is just what to come out. All these other extra things will not come out. So to get all these extra things to come out, you need to go and on that place in this. So now let's go to Pro Tools and upload our hex file. So you click open edit properties of this microcontroller, then this see upload hex file. So you put the directory that the hex file is on and press OK. So now the moment of truth, let's see if our system actually works as intended. So let's run the simulation. So far our simulation did not come out with any error, so it's good to assume that everything is going well. Now let's go and first reduce our temperature to a lower temperature less than 16 so that everything starts on. Now if you notice, as we started, the fan did not on. And if you notice, this was LED one is on because before it was in speed level one that was showing. That's why LED one, but now it has off because now it's below 16, which means at that point everything's actually off. Now let's first test our touch. Since our touch is not connected to our logical side of things, let's see whether our touch is working. So as you can see, our touch is not working. Do you know why? Because I actually made a very big mistake in connecting this touch. This is not actually meant to be ground. This is meant to be a power. Sorry, it's meant to be power, not ground. This is why we do simulation so that we can make our mistakes here and not in real life. Because if you do this in real life, it's possible that you might spoil something. So let's run this simulation and on this. So yes, our touch is working well. So you see that the touch lights are on, means our touch is working well. Now the reason why this LED is green by default and the reason why this sensor is not working without me on the switch is because this is a simulation software. So by default it already adds voltage to the microcontroller, and as long as this microcontroller is connected to all these other peripherals and this voltage source are already connected to all these other peripherals, by default it will to add voltage. But in reality, as long as they are all connected to themselves, just like they are in this circuit, other things will not on unless the switch is on. So let's on the switch. So far the switch is actually majorly controlling the fan because it's connected to the 12 volt directly. So let's on the switch. If you on the switch, you see that the fan does not stay on. Now let us gradually increase temperature to the different levels. So now when we go from 16 and above, that is level 1. So you see that our LED has on to indicate the level 1 connection, that we're in left speed level 1. And you can see our fan is rotating, but it's pretty slow for now. So let's go to level 2, which was above 25 degrees centigrade. So let's put at 26. So see that this fan speed is going to increase. So you see that the fan speed has increased compared to before. It's now faster, and the indication light is now also showing that we are now in speed 2. So you see that our program is actually working very well as intended. So now let's go to the highest speed, which is anything that is above 30. Let's put as 31. Now you see. So you see that the light is going to change. So now the light is now showing that we're in level 3. And if you notice, the fan is looking like it's rotating in reverse, but it's not really rotating in reverse. What is happening here is because you know when your fan is running very, very fast, like in reality, if you're looking at a blade that is running very fast, very, very extremely fast, sometimes it kind of looks like it's going in reverse. There's this kind of feeling. It looks like you're looking at it because of the speed it's running, it now makes it look like it's running in reverse. You know, it's running in this direction. So that's what it's trying to say. It's trying to show you that it's running extremely fast at this point. So that's why it's looking like it's reverse, but it's actually reverse. It's just trying to simulate that feeling that when you see a fan that's running very, very fast clockwise, it feels like it's rolling slowly in the other direction. That kind of thing. That's what it's actually indicating in this place. So you can see that our system is actually working very well, very, very well. So it means that we programmed this correctly and we did the hardware setup very well. To even kind of describe to you, let me describe to you that pulse modulation that we even talked about. Let me put an oscilloscope inside here so that we can really see the pulse width modulation in action. Let's connect this oscilloscope. So yeah, if I on this thing now, oscilloscope is meant to pop up. Yeah. Oscilloscope basically we use to read to see to visualize how signal is moving in our circuit. So for now, we connected the oscilloscope to channel A, and channel A is this yellow line. So let's on the fan. Fix it a bit. So let's on the fan to see how the signal for level 1 looks like. So now the fan, so you can see, so you see these are the signal looking like. So you see this positive what I was trying to explain for a pulse modulation is this line, this bottom line is 0 volts, while this top line is actually 5 volts. So it's trying to off and on and off and on, off and on, off and on, off and on and off and on in the particular manner. So basically, why it's doing this thing, it's going to limit the speed. So if for a slower speed, it will have longer offing time. If you notice, the line for offing is longer compared to the line for on. So for slower speed, they have a longer offing time and shorter owning time. So let's go to speed 2 and see how the signal looks like. So you see that the signal is going to change for speed 2, which so most of the time simulation software are actually slow based on using your CPU's load. So sometimes it takes time to react. But assuming this was real life, this thing was doing react very fast as it's doing, to reacting as fast as it's actually changing. It's just acting slow because we're actually simulating. So you see that now, what the fan is rolling at a faster speed, the off time is now shorter and the on time is now longer. So you see that it's now rotating at a faster. So you see that the signal has changed. Now, if you put it at its highest, it will just be flat out at this 5. It will not even be off at all again. It will just be flat out at this 5. If you let us see that, let's visualize that. Let's put that as its highest. We put that something at the highest, so you can see that is moving at is now completely 5 volts at the highest side. And if you put the temperature sensor to a point where the fan is going to off, you see that the signal will completely shift down to is zero. You see that shift down to zero, like there's nothing flowing again. So yeah, one more thing I'm going to do is just to add one more thing to make this circuit better, and that is actually a capacitor. Now, if you look at the circuit diagram, I actually added a 50 microfarad. I added a 50 microfarad capacitor. The reason why is to make that pulse modulation signal that we saw smoother. If I should add it to this circuit and replay that signal, you see what I'm trying to describe here. So let's go and add the capacitor. So smoothing capacitor is used for a lot of things, but one of the major things they use capacitor for in electronics is to smooth out signals. So let's add the capacitor. Add the capacitor. So you see the difference in signal now as I've added this capacitor. Oh, I didn't even change the value of the capacitor. It's in 1 microfarad, so you cannot really see. Let me just change the speed to the first one so that when it comes up, you will see the difference. So let's change the value to 50. 50 microfarad. Let's on this now and see and kind of see the difference. So far it's not really looking like, I don't think I changed that thing. Where let's change the value. Okay, sorry. What is happening is that we are reading the signal before the capacitor connection. So let's remove the capacitor from this side of and put it before the signal reading, so that the signal will read it after a capacitor has been added to it. Add the capacitor to the system. Let's change the value to 50 microfarad. Okay. Let's on the signal once again and see how it reads. Okay, so far it's on zero. It's like it's no signal. Let's increase the temperature. Let's increase the temperature to see how. So you can see that the signal is kind of getting more smooth compared to before. And the more you increase that capacitance value, the signal will be getting smoother. So it becomes like, I think this is good enough. And most of the time your signal is smooth, it will cause the fan to flow in a better. So you can see that there's a change in how the signal looks like. Change it to the height to the level 2. You see that the signal too. So you see that it's kind of more smooth. It's no more as sharp as square like before. It's now kind of more smooth. The transition is now more smooth compared to before. So yeah, so basically this is basically all for the training. So you see that we have learned a lot from this training. We learned basically how to design, things to consider when trying to design. We learned how to work with the hardware side of things. We learned how to connect that hardware to a software and how to talk with each other. But now we didn't, because of time and everything, we didn't like go in depth to how some things are done. But if you want to actually learn this embedded system very like in depth, you want to understand how to work with more projects, how to work with other various sensors, how to write the code, how to understand the code professionally. We are actually having a course coming up on the 19th of this month. Actually, I have a course coming up on the 19th of this month in GWS, that is getting dirty with embedded system, where we will train you for practically 2 months. That is from 19th of January to 20th of March on this embedded system. And you don't need to be, you can be anywhere and attend this lesson because it's actually on just like this practice now. It will actually be online and virtual. We'll work with simulation software and we'll actually work with the hardware itself. If you want the hardware, we can find a way to help you buy the hardware and ship it to you wherever you are. And if you just want to work with simulations, all our the projects that we selected to make with this course are projects that the simulation softwares, there are equipments in the simulation software that can actually help you simulate. Because one of the goals is that we want people to learn these things, and we don't want the fact that getting into hardware is expensive because you need to start buying things. You can actually learn these things without actually buying anything. You can me when I started learning these things, I actually first started working with simulation software, for instance, when I started my journey, and I think like 5 years ago or 3 years ago. I can't remember. I think it was 2022 I started learning all these things over there. But I started with simulation software. When I started saving up, I started buying this hardware to naturally start practicing what I simulated. And you will see that sometimes there are some changes. You might need to add some changes to what is simulated versus what is in real life. But they are very, at the end of the day, 90% of what you did in simulation is what you really do in real life hardware. So if you want to learn more on this thing, learn how, because this course covers a lot. We first even teach you basic electronics. And we first teach you electronics before we now even go in depth into the embedded system itself. So if you want to learn more about how to create things like this, how to create projects like this, you're an inventor, but you don't really know how to. You want to be an inventor. You have projects ideas in your head, but you don't really know how to go about how to create them. This course is for you, especially if they are focused into embedded system. And most of the field are going to, in fact, in this modern world, most of the fields are going to go into this engineering. You really need the knowledge of embedded system because everything now is now smart control. Everything is really smart control. Everything works these days with sensors or actuators to work. So this course is a course that can help you when they are venturing into robotics, whether you're venturing into UAV, that is drone, whatever you're doing, whether you just want to be in household electronics and things like that. This course is something that can really, really help you. So you can register for our course, and the registration is actually closing around the 15th of January. And yeah, and the course itself is starting 19th of January. So yeah, so with all that, thank you for attending our training. We're going to call it a day for now. See you next time because this Let's Build series we are doing in the hub is something we plan to do more often, at least once every 2 months or once every month in different fields. As now, for instance, now we do something in embedded system. Next time we can do something of just pure programming in Python or AI. Next time we can do something in computer aided design. Next time we can do something in different fields, in IoT, different things. So see you next time and always stay tuned to be updated, and you can join our community. The community link is down below. Community link is down below. The page link is down below. The course registration link is also down below. Everything you need. Also, the circuit diagram for this course is also going to be down below. So, in case you want to recreate this project, so everything you need is you can check the description of the video to see everything you need. So, thank you once again. I remain as one for Nika Chukuma. Thank you.